The digital world, with all its processing power, begins with one of the most common natural materials on Earth, sand. This raw silicon crystal is first grown into an ingot and then sliced into paper-thin, chemically patterned wafers. Fabricating these wafers requires massive facilities and extreme precision, maintaining tolerances down to the atomic level. But despite the sterile rooms and advanced manufacturing, the final processors are still physical objects, governed by unpredictable and chaotic laws of analog physics. Look closely at a finished silicon disk, and you will find billions of individual, microscopic components. This density creates an impossible cognitive limit. A human brain cannot design a functioning computer if it has to calculate the erratic quantum electrical properties of every single switch simultaneously. To bypass that limit, engineers use abstractions. They encapsulate complex, messy physical behavior inside a conceptual black box, yielding simple, predictable output. By stacking these boxes, they construct a hierarchy. Each level entirely hides the messy physical reality below it. The modern computing age was built on this premise. Engineers stopped worrying about the atomic foundation and focused their attention on the logical architecture above it. The lowest physical rung of this ladder is the MOSFET transistor. It operates as a basic switch where electricity controls the flow of electrons. To isolate these switches, those patterned silicon wafers are chopped up into individual independent chips, known as dies. The manufacturing process always yields some imperfections. Microscopic defects mean certain sections of the wafer inevitably fail testing and are discarded. Even with these defects, engineers pack millions of these microscopic switches onto a single die. This extreme density is known as very large-scale integration. Those fragile silicon squares are then embedded into larger ceramic packages with sturdy metal pins, allowing them to interface with the macro world. At this lowest layer, the environment is purely analog. It is plagued by voltage noise, leakage currents, and physical defects that cannot be completely eliminated. To tame that analog environment, engineers step up the abstraction ladder. They force erratic electrical energy to behave like a strict two-letter alphabet. This animated graph illustrates the mechanics. A specific low-voltage threshold is universally defined as a 0, and a high threshold is assigned as a 1. This binary system automatically filters out the noise. Any minor electrical fluctuation occurring between those exact thresholds is simply ignored. By discarding the continuous nature of physics, engineers create a discrete environment where flawless mathematical prediction is possible. Moving up to the next layer, groups of transistors are combined to apply 19th century symbolic logic to those ones and zeros. This truth table maps how basic logic gates, like AND, OR, NOT, and XOR, evaluate multiple input signals to produce a single calculated binary output. Wire thousands of these simple logic gates together, and you construct an arithmetic logic unit. The ALU is a massive block of hardware that blindly processes binary triumph over raw material. It takes the inherent unpredictability of a silicon switch and weaponizes it to perform pure, reliable mathematics. This schematic expands out to the system level. The ALU functions as one component within a larger orchestrated data path designed to execute software commands. During execution, it performs a subtraction test and outputs a 0 bit to determine if a software branch is taken. A programmer writing software never has to think about voltage or transistors to trigger this event. A modern computer is a towering stack of perfectly isolated abstractions designed entirely to shield human users from the quantum reality running their code. This leads to the most significant consequence of the abstraction ladder. The mathematical logic becomes entirely independent of the physical technology used to build it. Over decades of innovation, the physical footprint of these transistors has shrunk exponentially, doubling in density. Because the logic is firmly isolated, a 50-year-old circuit design functions exactly the same today, whether built with bulky vacuum tubes or modern silicon. Physical manufacturing will always eventually hit atomic limits, but the architectural design of a CPU operates in a realm of pure mathematics. The true miracle of computing is the conceptual blueprint. It is the framework that allows human logic to permanently conquer physical matter. Inside the microscopic architecture of a processor, you find a chaotic environment. Raw electrical signals surge through physical pathways, completely lacking any natural rhythm. The components doing math are combinational elements. They process data based purely on current inputs. The text points out a critical limitation. They have no internal storage and zero sense of timing. It takes physical time for inputs to propagate through logic gates. This creates a physical bottleneck called propagation delay. While those electrical signals are traveling through the gates to calculate an answer, the intermediate voltages fluctuate wildly and unpredictably. If another component further down the line attempts to read the signal while it is still transitioning through these fluctuations, it absorbs corrupted, invalid data. The logic fails. A processor running purely on combinational logic is too unstable to be useful. To compute reliable data, the hardware requires a physical mechanism to impose order on the flow of time. The first part of the solution is building a physical dam inside the processor, a structure to catch and stabilize those fluctuating signals before they interfere with the next calculation. These dams are called state elements. As the definition shows, these are memory components like registers that contain internal storage, giving them the ability to catch a signal and hold it indefinitely. Unlike combinational logic, state elements characterize the computer's memory. Because they can trap a voltage, their specific values can be safely saved, read, and restored at a later time. But while state elements provide the memory to hold the data, they do not manage the timing. Without a master conductor telling them exactly when to open and close their gates, the electrical signals still collide. That conductor is the clocking methodology. This set of rules defines exactly when state elements read incoming signals and write them out. It prevents a specific failure. If written at the exact same time it is read, the resulting value could be an unpredictable mix. To enforce these rules, engineers use a master clock. It is a continuous, rigid electrical pulse distributed across the hardware grid that forces every isolated component into a single synchronized rhythm. The discrete time interval between these pulses is called a clock cycle. It acts as the fundamental unit of time for the entire machine. The clock does not compute data. It enforces a mathematically consistent rhythm onto the messy physics of the hardware to ensure system stability. By zooming in on the interaction between a single state element and the clock pulse, we can see how this rhythm governs the logic. The specific rule governing this interaction is the edge-triggered clocking methodology. This graph illustrates the clock wave. The defining moment is the rising edge, the exact microsecond voltage transitions from low to high. Because of edge triggering, the state element's gate remains shut, ignoring fluctuating data, until that precise rising edge strikes. This mechanism slices a continuous stream of analog voltages into perfectly ordered, discrete digital moments. This figure illustrates a complete computing step, combinational logic sandwiched between two state elements. We trace the signal as it leaves the first state element, is processed by the logic block, and arrives at the second. This establishes the speed limit of the computer. The clock cycle must be long enough to allow the slowest electrical signal to propagate and stabilize before the next edge hits. This configuration allows the processor to update a memory register based on its own previous value, without triggering a destructive infinite feedback loop. As the text explains, edge triggering resolves this potential conflict. Because state elements only update on the clock edge, the system can read the old data and prepare the new value in the same cycle, without the signals bleeding together. In motion, this creates a synchronized loop. Data is modified by logic gates and securely caught by the next register exactly when the pulse strikes. By controlling these microscopic windows of time, engineers created the predictable timing required to build complex, reliable computing systems out of raw electricity.
Look at a line of code on a computer screen. It is just text. On its own, that static string of letters and symbols has zero ability to physically change the real world. But to perform an actual task, to render a video frame, update a database, or send an email, that abstract text has to somehow cause the physical movement of electricity through solid hardware. The bridge between code and electrical reality is the central processing unit. If we dive inside the casing, we find the physical engine executing software. Looking at the silicon architecture, the processor is divided into two main halves. The first is the data path. This is the physical brawn of the operation. the dense grid of logic blocks where the arithmetic and calculations actually happen. The data path needs direction, which comes from the second half, the control unit. Think of this as the brain that dictates exactly what the data path, memory, and output devices should do, based entirely on the software's instructions. To understand how our digital tools operate, we have to track a single instruction as it navigates this physical, microscopic maze. The journey begins with a single clock cycle. This is the rhythmic pulse that orchestrates every step of the workflow, moving data from one stage to the next in exact physical sequence. This diagram shows the specific pathways involved. On the left, the program counter acts as a locator, pointing to the memory address of the next instruction waiting in line. Once identified, the instruction is extracted from the memory block, bringing it onto the data path. The moment it arrives, that 32-bit package splits. It sends distinct electrical signals racing to both the register file, where data is stored, and the immediate generator at the exact same time. The instruction is now inside the processor, but it is raw data. Before math can happen, the chip has to physically route these signals through the correct channels. As electrical data moves across the chip's buses, the paths are not straight lines. The signals frequently hit intersections where multiple routes are possible. Positioned right at these intersections are physical electronic steering gates, called multiplexers or data selectors. A multiplexer receives multiple data inputs from different sources, but it relies on a specific binary control signal to decide which single path is allowed to proceed forward. These multiplexers function as a dynamic switchboard, allowing the processor to rewire its own physical pathways in real time to meet the specific requirements of the instruction. What authority provides the binary signals that tell the multiplexers which lanes to open? In this architecture diagram, the signals originate from the large blue oval at the top center. This is the main control unit, the processor's brain that intercepts the incoming instruction to direct the data path. Notice the line flowing directly from the instruction bus into that blue unit. The control unit only needs to read the lowest 7 bits of the instruction, the opcode, to identify the exact mathematical operation the software wants to execute. Once it reads that opcode, the control unit fires specific electrical signals, like read-write or ALU/SRC, along these blue control lines, locking the multiplexers across the data path into their correct positions. At this precise moment, an abstract line of code has been successfully translated into a physical hardware configuration. The entire processor is completely wired for one specific command. While the main control handles the broad pathways, it delegates the precise mathematical instructions to a smaller, localized control unit positioned right next to the ALU. The main brain does not send the entire command. It only transmits a basic, high-level 2-bit signal to this secondary unit. That localized ALU control then merges that 2-bit signal with the instruction's unique formatting fields, generating a highly precise 4-bit operational code specifically for the ALU. This multi-level delegation keeps the processor fast. The heavy-lifting data path gets the precise, detailed commands it needs without bottlenecking the main control unit in the process. With the pathways set and the command received, the ALU executes the mathematics perfectly, outputting the newly calculated physical data. That resulting data travels through one final multiplexer to be written securely back into the register file. The single instruction cycle is complete. The static code has manipulated physical reality. If we zoom out from this isolated loop, we can view the true scale of what is happening. This orchestration, fetching, decoding, steering, and calculating, happens continuously. Inside a standard 1 GHz device, this microscopic choreography occurs over 1 billion times every single second. Every video game, global network, and AI system running today relies entirely on the flawless, high-speed repetition of this microscopic interplay between brawn and brain. At its core, programming presents a massive translation problem. Humans write in structured, abstract logic, using concepts like loops, variables, and abjects. Hardware understands none of that. A physical CPU only recognizes electrical states, voltage high or voltage low. To bridge that gap, we need a translator. There are 2 ways to do this. You can use an interpreter, which translates and executes the code line by line while the program runs, or you can use a compiler, which analyzes the entire program ahead of time, translating the whole abstract source code into an optimized machine-level executable. Historically, compilers were monolithic. A team would build one compiler to translate C++ for an x86 processor. But as new languages like Rust or Swift emerged, and new hardware like ARM processors took over, this created an unsustainable n times m complexity problem. Building a custom compiler for every possible combination requires an impossible amount of duplicated effort. The modern solution is the phase-decoupled compiler. The pipeline is split into 3 distinct tiers: a front end, a back end, and a universal middle end connecting them. To see how this pipeline actually works, we can trace a single piece of logic from human intent down to silicon. Take a basic C++ statement, int x equals a plus 10. Transforming this simple equation into physical execution requires a process of sequential reduction. The compiler must strip away all human context, layer by layer, until only absolute mathematical certainty remains. When the front end first looks at our code, it doesn't see an equation. It is entirely blind to the logic. It sees a flat, one-dimensional array of raw characters, including spaces and semicolons. This diagram illustrates the first step, lexical analysis. The lexer scans that raw text, deletes the meaningless whitespace, and groups the remaining characters into functional categories called tokens. You can see the string separated into a keyword, identifiers, operators, and a literal. To do this at high speed, lexical analyzers operate as finite state machines. They read the character stream one letter at a time, instantly changing state to match the sequence against the strictly defined rules of the language. It is critical to distinguish the raw text from its new categorized state. The physical characters int form the lexeme, but the lexer identifies its structural role, tagging it as a keyword token. Through lexical analysis, a continuous string of text is converted into a discrete sequence of structural building blocks. The raw input is now ready for grammatical assembly. Those categorized tokens are then passed to the second phase of the compiler, syntax analysis, performed by a parser. Here we see the parser applying the language's strict grammatical rules to that flat sequence of tokens. The blocks shift and stack, connecting into a branching structure called an abstract syntax tree, or AST. Notice how the operators, the equals and the plus signs, become the parent nodes dictating the hierarchy. For decades, compilers relied on bottom-up, table-driven parsers generated by tools like Flex and Bison. These parsers shift tokens onto a stack until a reduction rule matches, making them highly memory efficient but incredibly rigid. Modern language tooling often utilizes top-down, recursive descent parsers. These build parent nodes before their children and utilize an adaptive look-ahead capability, evaluating arbitrary amounts of upcoming tokens to resolve complex grammatical ambiguities. As the tree takes shape, it actively discards purely syntactic noise. Semicolons, commas, and parentheses are required for human readability, but they are unnecessary here. The AST preserves only the operational logic. By the end of syntax analysis, the compiler has extracted the mathematical intent. It now holds its first purely structural, logical representation of the programmer's code. Look at this line of code. Grammatically, this is perfectly constructed. It has a keyword, an identifier, an assignment, and a literal. The parser will accept it. But mathematically, it is impossible to assign a text string to an integer variable. It is a fatal semantic error. This is why the final stage of the front end is semantic analysis. The compiler traverses the newly built abstract syntax tree to enforce type checking and confirm that all variables are accessed within their valid scopes. To track these rules, the semantic analyzer relies on the symbol table, visualized here as a translucent stack of hash maps overlaying the AST. As the program enters a new block of code, a new map is pushed onto the stack to record local variables, and then popped off when the scope exits. This stack design manages variable shadowing. When the compiler needs to resolve an identifier, it searches from the top of the stack, the local scope, and works its way downward to the global scope, ensuring the correct variable is referenced even if multiple variables share the same name. Once the semantic checks pass, the translucent symbol table merges directly into the nodes. Our tree is now an annotated AST, permanently tagged with strict metadata labels like data types and visible scope boundaries.
Passing this semantic gateway proves the program is logically sound. The language-specific front end has finished its job, and the code is now prepared for universal optimization. The code now enters the middle end, which is built around an intermediate representation, or IR. In the industry-standard LLVM framework, this IR acts as the universal bridge that solves the scaling problem from earlier. All front ends translate into it, and all back ends translate out of it. Watch as the branched, language-specific annotated AST collapses. It flattens into a linear, target-independent sequence of text-based instructions known as LLVM IR. To optimize this code, LLVM IR relies on one specific architectural feature: static single assignment form, or SSA. SSA enforces a strict foundational rule. Every variable in the intermediate code is assigned a value exactly once. If a variable's value needs to change in the original source, the IR simply creates a brand new, sequentially numbered version of that variable. By eliminating reassignment ambiguity, SSA transforms standard sequential code execution into an explicit mathematical data flow graph. The text instructions morph into nodes, and the unidirectional arrows map the strict dependency of the data moving through the program. Because a variable in SSA can never be overwritten, the compiler can track exactly where a value is created and exactly where it is used. This strict tracking unlocks aggressive, highly reliable code optimizations. For example, the compiler performs constant propagation. If it sees that a variable is assigned a static number and then added to another static number, it simply calculates the math itself during compilation, replacing the variables with the final result. Then it performs dead code elimination. By analyzing the data flow graph, the optimizer identifies isolated nodes whose results are never actually used. Those useless nodes are pruned away, and the remaining data flow edges snap together to bypass the deleted instructions. These are purely algorithmic improvements. The middle end is streamlining the logic independently of the original C++ source code, and without needing to know anything about the hardware that will eventually run it. The middle end has distilled the programmer's intent into its purest, most mathematically efficient algorithmic state. But pure mathematics cannot execute a program. As we enter the back end, the compiler confronts the physical limitations of the target hardware, the CPU's silicon architecture. The first step here is instruction selection. The back end translates the universal LLVM IR operations into the specific instruction set architecture, or ISA, hardwired into the processor. A single mathematical operation in the intermediate representation might require completely different physical instructions depending on the chip. Adding two numbers on an Intel x86 processor involves different hardware constraints than doing the exact same addition on an ARM chip. Once the hardware instructions are selected, the compiler performs instruction scheduling. It strategically reorders the tasks to keep the CPU's execution pipelines constantly fed with data, preventing bottlenecks and physical hardware stalls. The backend's primary job is mapping the perfect mathematical logic of the optimizer onto the imperfect, constrained physical reality of the machine. To execute those instructions, the CPU needs memory, but it doesn't use the computer's main RAM for immediate calculations. It uses internal storage banks called CPU registers. These are the absolute fastest form of memory, but they are strictly limited in number. This creates the register allocation problem. The intermediate code assumes it has an infinite supply of variables. The backend must map that infinite software demand down to a fixed finite number of physical hardware registers. To solve this, the compiler builds an interference graph. In this diagram, every variable is represented as a node. The edges connecting them form whenever two variables must be live, or actively holding data, at the exact same time during execution. The compiler applies graph coloring to assign registers. It fills the graph with a limited color palette, each representing one CPU register. The strict rule is no two connected nodes share a color, as they exist simultaneously and need separate storage. If the graph requires more colors than there are physical registers available on the chip, the compiler triggers a spill. It is forced to degrade performance by pushing the excess variable data out of the fast CPU registers and into the much slower main RAM. This final step completes the journey. To solve the translator's dilemma, the compiler has taken abstract human logic, broken it into structural tokens, built it into grammatical trees, and refined it into mathematical graphs. All of these complex transformations orchestrate the exact microscopic firing of voltage gates across a slice of physical silicon.